Hi guys, today I'm going to discuss one of the problems from MIT B problem in 2017. Here is the problem. The problem is to compute the limit of an integral. The first integral I1 is defined to be 1 over 1 plus root x dx. Second one is I2 is the 1 over 1 plus 1 over 1 plus root x dx. I3 is 1 over 1 plus 1 over 1 plus 1 over 1 plus root x dx. Of course, these are all the integral from 0 to 1, from 0 to 1, from 0 to 1. And like you can guess, I4 now, from 0 to 1, 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus root x dx. And so on. So if you define in this way, what is the limit of n goes to infinity? So that's the question in this problem. Before that, I would like to discuss the Fibonacci sequence. Fibonacci sequence is a special sequence. So A1 is 1, A2 is 1, A3 is the sum of the first and second term, like A1 and A2, which is 2. A4 is sum of A2 and A3, previous two sequence items in here, 1 plus, so it is 3. A5 is sum of A3 and A4, which is 5. A6 is 3 plus 5, 8, and so on. So this is called Fibonacci sequence. So we know that this is the sequence defined that way. One of the most important property is an plus 1 is equal to an and an minus 1 for n greater than or equal to 1. So if you prove, you can prove that limit of the ratio in here, if I look at the limit n goes to infinity, an plus 1 over an is the number, it turns out to be 1 plus square root 5 divided by 2. This is called the golden ratio. It's very easy to compute the limit in here. I'm not going to prove that. So using this Fibonacci sequence and this, how can we evaluate the integral in and then pass the limit as n goes to infinity? Alright, so let's go back to our integral I1. But before that, I would like to define sequence of functions. For example, let's say f1 of x is 1 over 1 plus root x. f2 of x, I'm going to define f2 of x to be 1 over 1 plus f1 of x. In general, I'm going to define fn plus 1 in here of x to be 1 over 1 plus fn for n greater than or equal to 1. For example, f2 becomes this, and if you simplify that, 1 over 1 plus 1 over 1 plus root x, so it's easy to simplify this, and you can get 1 plus root x divided by 2 plus root x. f3, you can get 1 over 1 plus f2 of x using this formula in here. And this initial one. And then we plug this f2 in here. So 1 over f2 is 1 plus root x divided by 2 plus root x. And you can simplify this to 2 plus root x divided by 3 plus 2 of root x. And then similarly you can calculate f4 of x. One over 1 plus f sub 3 of x equals now 1 over 1 plus, just plug it in here, 2 plus root x over 3 plus root x. So this turns out to be 3 plus root x divided by 5 plus 3 root x. So for example, I can observe that like a3 in here is a4. I can write this as a4 plus 2 is a3 of root x divided by 5 is a5 plus a4 root x. So this is f of 4. Similarly, this one now, this is a3 plus a2 root x divided by 3 is a4 plus 2 is a3 again, a3 root x. You can just write it that way. That one, a2 plus a1, both of them are 1, divided by a3 plus a2 root x. Okay, so when you have 2 in here, so you have 2, 2. When you have 3 here, f3, you have 3, 3, and then 1 more. If you have 4, 4, 4, and then 1 more in here. In general, if you define f5 of x to be, like you can guess the next one, it turns out to be a5 plus a4 root x turns out to be divided by a6 plus a5 root x. Alright, and so on. You can write this. In general, fn of x is going to be an plus an minus 1 root x divided by an plus 1 plus an root x. Okay. So I have this. Why did I observe this? Because I1 is integral of f1. Right. I2 is the integral of f2, which is from 0 to 1, of course, from 0 to 1, which is f2 becomes 1 plus root x divided by 2 plus root x dx from 0 to 1. I3 is from 0 to 1 f3 of x dx. And then from 0 to 1, 2 plus root x divided by 3 plus root x dx. And so on. So if you write in general using this fn from 0 to 1, fn of x dx, and it's going to be from 0 to 1, an plus an minus 1 of root times root x divided by an plus 1 plus an root x dx. Just because, like, in general you can just see that now this is from 0 to 1, a3 plus a2 of root x divided by a4 plus a3 of root x dx. And you can write more like this, an. So what is the limit of this? Limit n goes to infinity of an would be the limit n goes to infinity from 0 to 1, an plus an minus 1. Actually, limit of in is the limit of this sequence, and then you integrate, sorry. So we should put the limit inside then. So it's the limit of fn of x and goes to infinity from 0 to 1. You just calculate this and then integrate. That's what in is. Alright. So it's going to be from 0 to 1, limit n goes to infinity. This is an plus an minus 1 root x divided by an plus 1 plus an root x dx. So let's compute this limit first. Okay, like from 0 to 1, I'm just going to rewrite it. Limit, and then pull an out. If you pull an out, you get 1 plus an minus 1 over an root x. And then in the denominator, if you pull an out, so an plus 1 over an plus root x dx. So if you pass the limit here, this one goes to 1 over phi. From 0 to 1, 1 plus 1 over phi root x divided by, this is phi plus root x, golden ratio number dx. Like phi is in here, 1 plus root f5 divided by 2. In this case, if you simplify this expression from 0 to 1, phi plus root x divided by phi plus root x dx. So basically this is from 0 to 1, 1 over phi dx. What is 1 over phi? From 0 to 1, 1 over 1 plus root 5 over 2 dx. So it is going to be 2 over 1 plus root 5, or you can just multiply both sides by root 5 minus 1, root 5 minus 1, and then you can write this as 2 times square root 5 minus 1 divided by 5 minus 1. You can say square root 5 minus 1 over 2 is the limit of in, and goes to infinity here. This is the final answer. Thank you for watching. See you in the next video.